Okay, good evening. Well, we're back together again. We're working on our general class upgrade class, and we are in the second half of chapter 4 for tonight. And I always like to say in the beginning, if there's anybody that has found us by accident on YouTube or whatever, I highly recommend that you go back to find the playlist for this class series and start out with lesson number 1, because they build on one another. That'll get you ready for chapter 4, which is where we are tonight. Now, I put this up last week as well, the ARRL Chapter 4 resources. We're going to be going through a couple of things very quickly tonight. Not so fast you won't catch them, but you might be wondering, well, is there more background behind all of this? Well, you'll find that background. Some of it's in our license manual, but there's a ton of good resources out here on the ARRL site. You don't have to be a member to access these resources, by the way. So if you want to dig a little deeper, that's the way that you can do it. We've got 58 pool questions spread throughout this half of the chapter. So we're going to jump into it. First of all, I'd like to do a little bit of review, though. We talked about Presley, Paco, and Emily last week. And just to kind of reinforce that or maybe clarify some of it, first of all, I've got this real scary word down here that says memorize, okay? This will help you for those that want to get 100% on your exam. If you can just remember these silly little things here, that will decode all of the formulas that you need to do all of the math questions in Chapter 4. So Presley is an insane, irritated raccoon. He kind of looks like he's on drugs or something. Paco is a playful elephant, energetic elephant hiding on top of the refrigerator. And Emily, we said, was she had a master's degree in public relations, so her company considers her as the root of public relations. Now, how does all of that silliness translate? Well, these are the 3 new formulas, and they are on our general class reference sheet, which we'll look at in a minute. But Presley, P, it's an insane, irritated raccoon. I times I, which is I squared times R. And the rest of these work the same way. Now you'll notice here in the formulas that each one has an R in it. That was new for the general class. So the way that we figure these out is that we go through a sequence of asking what's going on, what are we being asked for, and then which formula happens to include I in R, or E in R, or P in R. So first scary word, see if you can memorize these. Secondly, see if you can write these out then in 30 seconds. And if you need to, go ahead and include these as part of your memory dump sheet. And so the sequence is, what are we asking for? Power, voltage in the question. What's given? If we're given current and resistance, we know this is the formula you have to use. If we're given voltage and resistance, notice every one of these is unique, and then we have to use this formula. So you have to match up these formulas with what we're given to decide which one is the correct formula to use. And then of course there's one problem that just uses the pi magic circle. If you remember PIE, power equals current times voltage. So what I want to do now is go over to the calculator cam and look at the general class reference sheet, which we have shown here. And I'll comment that everything on this sheet happens to be things that we covered last week, believe it or not. So now you've got somewhat of a grasp of everything that's here. We talked about our ear and pi circles. We talked about our new formulas. We haven't talked about reactance tonight. That'll be one of the first things we talk about. We covered peak to RMS conversion, and the only thing you really need to know about decibels, the 20% decrease for a decibel value of 1. So I hope that's starting to feel a little bit good. We did a lot last week. Now I'd like to jump over to this handout, which we looked at briefly last week. You have a handout from last week says General Class Chapter 4 calculation questions. Now the 13 questions that are in this chapter that involve calculations are all here, so you can test your ability to apply the formulas. The first one here is G5BO3. How many watts of electrical power are used? So what are we looking for? Power. 400 volts DC is applied to an 800 ohm load. Well, we've got voltage and resistance. So if you've memorized your formulas, if you've got voltage and resistance, that would be PACO, E squared over R. Then we go through actually how to do it. And because all of the problems are in this one handout, you can go through and exercise your ability to solve those. So I wanted to just bring that to your attention by way of review. We'll get right into the material for the second half of this chapter, reactance and impedance. I put together this chart because to me it was very helpful. We talk about resistance, reactance, and impedance. All of these are entities that represent opposition to the flow of AC current. Pure resistance, we understand. R, resistance, measured in ohms. Does it vary with frequency? No, it does not. And this is the same as DC resistance. Now the two new ones for tonight, for our chapter, reactance and impedance. Now reactance can be capacitive or inductive. We'll talk more about that. It's symbolized by the letter X. Capacitive reactance is X sub C. Inductive reactance is X sub L. It also is measured in ohms. Notice that all three of these forms of opposition to the flow of AC current are measured in ohms. That implies something, and what it implies is that you can use the Ohm's law formula, sometimes with some modification, to solve any of the problems related to reactance and impedance. It can be kind of confusing at first until you realize that the opposition to the flow of AC current is always measured in ohms. Reactance does vary with frequency. So it varies with frequency, yes. Reactance is unique to AC. Value changes with the frequency. Now it acts a little bit different between capacitive and inductive reactance, and we'll show you that coming up. But it's still opposition to the flow of AC current measured in ohms. And then the third concept is impedance. It's a combination of resistance and reactance. Here we had pure resistance. We were talking about pure reactance, only the effect of a capacitor or an inductor. Now if you have resistance and reactance, that's called impedance, signified by the letter Z, measured in ohms. It also varies with frequency. So having all of this in one table was really helpful to me. So now let's talk about reactance. Make sure I get this, here we go. All right, so reactance is the opposition to the flow of alternating current caused by capacitance or inductance, capacitors and coils. Blue text, remember what that means. Now the symbol for reactance is X. X sub C, capacitive reactance, X sub L for inductive reactance. Now how can you remember that the symbol is X? Well, if a big scary bear suddenly jumped out of the woods and was facing you, attacking you, you might cross your arms in front of you to protect yourself. That can think of that as being the X, crossing my arms to protect myself from the scary bear. So the symbol for reactance, I'm reacting to something by crossing my arms, an X. Reactance is measured in ohms, like resistance. We saw that on the previous slide. In these formulas, you don't have to solve anything using these formulas. These are the two other formulas that are on the general class reference sheet. But I'd like to point out the difference between a direct relationship and an inverse relationship. These formulas are somewhat similar. X sub L, inductive reactance. The formula is 2 pi times frequency times L. L is inductance measured in henries. So a direct relationship means that if something increases on this side, this is going to increase as well. So if we want to increase the inductive reactance, we can raise the frequency, or we can increase the inductance. That's the direct relationship. The inverse relationship, which works with capacitive reactance, means that if you increase any of these values, frequency or capacitance, you're going to decrease the capacitive reactance. So that's the concept of a direct relationship in an inverse relationship. We have this reciprocal here, 1 over something. So if this gets bigger, that gets bigger. If either of these get bigger, this gets smaller. There's two pool questions related to that, so that's why I'm recommending, if you can, go ahead and memorize these two formulas as well. So as frequency increases, X sub L increases. We talked through that. As frequency increases, capacitive reactance decreases. So we need this for some questions coming up. Now here's some interesting graphs. We've got reactance in ohms over here and frequency in hertz. So this happens to be an audio frequency example. And we can see that the inductive reactance starts here, and as the frequency goes up, it eventually becomes very high. The capacitive reactance starts high and gets smaller and smaller as frequency goes up, eventually becomes low. There's one magic point here where the two lines cross. So at 50 hertz, the X sub C and X sub L are exactly the same value, which is about 30 ohms. That's a magic point in ham radio called resonance. That's going to be very, very important as we move forward. All right, with those principles highlighted, I think you can answer all of these questions now. What letter is used to represent reactance? And you can unmute and give us it is Bravo. And let me caution you not to get this letter confused with this one, because it'd be easy to make this mistake. All right, so just a caution. What unit is used to measure reactance?
Ohms.
It's the ohms. Bravo. What is reactance? Now they come at this from all different directions, so just bear with us because these are all pool questions.
Bravo.
It is Bravo. Opposition to the flow of alternating current caused by capacitance or inductance. That's reactance. Which of the following is opposition to the flow of alternating current in an inductor?
Delta.
It is delta. See, they're coming at us from different ways, and you feel like this is supposed to be a trick question, but it really isn't. Okay, which of the following is opposition to the flow of alternating current in a capacitor?
Alpha.
Well, it's actually reactance again. Yep.
Yeah.
So yeah, like I said, yeah, cross your arms and look out for that bear. That's reactance. So the opposition to the flow of alternating current in a capacitor or an inductor is reactance. How does an inductor react to AC? Here's where we need to know those relationships. An inductor, and that formula was X sub L equals 2 pi frequency L, which is the direct relationship. And with a direct relationship,
D.
it is D. Yep, with a direct relationship, as the frequency of the applied AC increases, the reactance increases. So the inductor has that direct relationship. The capacitor has an indirect relationship. Oh, guess what? That's the next one. How does a capacitor react to AC?
Alpha.
Did I hear an alpha?
Yeah, alpha, sorry.
Okay, as the frequency of the applied AC increases, the reactance decreases, and that formula is X of C equals 1 over 2 pi frequency C. So if you can understand that direct and indirect relationship and remember the formula, you'll be able to get these two. You won't get them confused. Resonance, that magic point where capacitive and inductive reactance happen to be the same at a specific frequency. So resonance in a circuit occurs when capacitive and inductive reactances are equal. So we've got a diagram over here. We don't know what frequency this is, but when the inductive and capacitive reactances are equal, something very magical, very freaky and mind-blowing happens. In an LC circuit, inductive and capacitive reactances cancel at resonance. So if this and this are going to cancel, the ohm value is going to go to 0, right? 0 ohms. So in a resonant circuit, the reactances of L and C cancel, forming a short circuit, leaving only the resistance R as the circuit's impedance. And I can kind of illustrate that for us here. I'm going to draw from the top of the coil. Oops.
Hang on. I can. There you go.
There we go. So we're going to make a connection here. They cancel. It becomes 0 ohms resistance. So the only thing in the circuit happens to be the resistor. So we would have maximum current through this circuit when we reach the point of resonance. Seems very, very odd, doesn't it? So when inductive and capacitive reactance are equal in a series LC circuit, which this is, resonance causes impedance to be very low. I said it was like a short circuit. Their definition of very low is what I'm calling basically a short circuit. Now, why is this valuable? Well, as the frequency varies, you can see that we're starting to get the concept of selectivity. We can use this concept in tuned circuits to pass certain frequencies or reject other frequencies to allow you to differentiate between different signals on the band. Now we're going to talk a little bit about parasitic inductance. We included this last week as well because our friends at the ARRL put this pool question in the wrong section. So we needed to cover it in both places for you. So some of this will be repeat. So parasitic inductance, that's inductance that you don't want, like you don't want a mosquito biting on you. So parasitic is an unwanted characteristic resulting from the component's physical construction. And in this case, we're talking about a wire-wound resistor on a ceramic form. So nichrome wire is wire that has a certain amount of resistance per inch. So if you wrap enough of that wire around a ceramic form, you can make a resistor of different values, depending upon how much wire is on it. But that's a problem because that wire-wound resistor looks like a coil and acts like a coil electrically. So a reason not to use wire-wound resistors in an RF circuit, the resistor's inductance could make the circuit performance unpredictable. So you might want 100 ohms of resistance, but all of a sudden you've got some inductive reactance there too, which could really foul things up. So RF circuits, radio frequency circuits, normally use non-inductive parts, such as carbon composition resistor, carbon film, metal oxide, which have very low inductance. So that's just this little piece here we have to watch for. Now here's some amazing information. Here's a coil, and you notice these little bitty capacitor things between each turn. So a coil, even though it will act as an inductor with inductance, there's also some capacitive effects going on at the same time. So the space between the turns on an inductor have a small amount of parasitic capacitance, becoming smaller at higher frequencies. Inductive reactance becomes larger at higher frequencies. At some point, you can imagine that they're going to cross. At some frequency, the inductive and capacitive reactance will be equal. This is the point of self-resonance. All right, watch what happens next now. Above the self-resonant frequency, the inductor will become capacitive. So yikes is right. So we thought we were dealing with a coil here, and above this self-resonant frequency, this thing we thought was a coil becomes a capacitor. So that's pretty weird. Now, do you need to worry about this? Well, if you're making your own equipment, building your own equipment, then you probably do. But our friends that manufacture our radios have taken all of these effects into account for us. So if you're using a purchased radio, the engineers have already worked through this. But we need to grab this principle here because there's a pull question about it. Speaking of which, what occurs in an LC circuit at resonance? Several things do, but there's one particular one here in the answers.
Delta.
It is the delta. Inductive reactance and capacitive reactance cancel. What happens when inductive and capacitive reactance are equal in a series LC circuit? Surely, resonance causes impedance to be very low. Why should wire-wound resistors not be used in RF circuits? Bravo. The resistor's inductance could make circuit performance unpredictable. What happens when an inductor is operated above its self-resonant frequency? It started out as an inductor. Charlie. It becomes capacitive. Exactly. Yikes is right. So, all right, so we're moving on to the next concept here called impedance. So we've talked about pure resistance, we've talked about reactance, a coil or a capacitor by itself. Now what happens when we combine resistance and reactance? Okay, that's something called impedance, combination of resistance and reactance. All of these funny terms here. So the symbol for impedance is Z. And I'll show you how to remember that in a minute. Measured in ohms, and varies with frequency, and it's unique to AC because the value will change with frequency, only with an AC circuit. Again, impedance, opposition to the flow in an AC circuit, combination of resistance and reactance, denoted by Z, the letter Z, and it's measured in ohms. The inverse of impedance is called admittance. I'll give you maybe a way to remember that as well. And impedance is the ratio of voltage to current. Well, let's see if we can kind of noodle this one out. So here's our famous Ohm's law formula, EIR. Resistance, of course, is measured in ohms, but in AC, the opposition to the flow of current is measured in Z. So this same formula would apply. Therefore, impedance is the ratio of voltage to current. So impedance, or Z, remember how we do this? You put your thumb over this part of the circle, and we've got E over I. So here we've got a ratio of voltage to current. And now hopefully these words will make sense. Impedance is the ratio of voltage to current. Here's a black box, just illustrating some values. We know that we've got a current flow and a voltage. We don't know what's in the black box, but given the values that we have here, we can see that the impedance happens to be 125 ohms. So they won't ask you to calculate one like this. This is just an illustration. And now to something I think will be helpful. I just thought of this today. Think of a door. We've got a closed door and an open door. Now, why do you suppose we have a Z on the door representing impedance? Well, because there's a zebra behind the door, okay? So hang on, it gets better as we go here. So when the door is closed, we are impeded from going through, all right? When the door is open, we are admitted to pass through the door. So if you can remember this silly little diagram here, admittance is the inverse of impedance. Over here it says in the blue text, the inverse of impedance is admittance. Symbol is Y, but they don't ask us that. I don't know why. And we already saw that impedance is the ratio of voltage to current. So if you can remember my silly little memory trick here, hopefully you can remember that Z is the symbol for impedance. You're impeded by a closed door, and there's a zebra behind the door. That's why it has a Z on it. You're impeded from
I don't know. I don't think that zebra once it's coming through the door.
Well, we might want to go through the door and pet it, and we would be admitted so that we could. So if you can kind of capture that picture, you won't be tripped up by the questions. And this all,
Sure that's not a yak?
no, that's a zebra because it's got
Why?
stripes on it. Yeah, got stripes.
A
on it.
yak or Y?
Yeah. All right. We better move on or we'll be here all night. Exam questions on impedance. All right, what is impedance?
Alpha.
Well, is it the product or is it the ratio?
C.
It is C, the ratio of voltage to current, or E over I. Yeah.
Oh.
You were close, but no cigar. What is the term for the inverse of impedance?
Yak.
Delta.
Yeah, delta impedance. Very good, very good. Well, maximum power transfer occurs when the source and load impedances, well, we're moving on to another section now, impedance matching, and this is just a little factoid. Maximum power transfer occurs when the source and load impedances are equal. So that's a key principle. We're going to be talking about it here and in the extra class when we all get there. Amateur transmitting equipment is designed to have a 50 ohm output. So your transmitter, if you've got a transceiver, it is expecting, its output impedance is designed to be 50 ohms typically. Most antennas are designed to have a feed point impedance of 50 ohms, but rarely present that impedance over the whole band, especially 80 meters and 10 meters because the band is so wide. And you may remember, or you'll hear this when Gary does his antenna chapter, that the impedance of a dipole is about 73 ohms. So we've got a little bit of a mismatch there with a dipole. We've got a 50 ohm transmitter, 50 ohm transmission line, and a 73 ohm antenna. And we'll be talking about how to, some ways to resolve that. That turns out to be less than a 2-to-1 SWR, which transmitters usually don't care about. And the reason that this is important, the reason we're getting into all of this is because modern transceivers will, if they sense a high SWR due to a mismatch, they'll start folding back the power to protect the transmitter. So that's why this is important. So a reason to use an impedance matching transformer at a transmitter output is to present the desired impedance to the transmitter going in that direction and the feed line in the other direction. So the whole reason for impedance matching here is really, boil it down, it's to keep the transmitter happy, to think that it's seeing 50 ohms. So here we have a transmitter, 50 ohms, some kind of an impedance matching circuit, and then the feed line antenna. In this case, it says 600 ohms, so we have to do something fancy here in order to make the transmitter think that it's connected to a 50 ohm load. And we'll talk about some ways that we can do that. The maximum transfer of power is what we're trying to achieve, and 50 ohm presentation to the transmitter. So here's some examples. So transformer turns ratio. Okay, remember we talked about transformer turns ratios. We were talking about step up and step down transformers. Okay, we're going to extend that a little bit with impedance matching. So transformer turns ratio that matches an antenna's 600 ohm feed point impedance to 50 ohm coaxial cable is the case we're going to consider, right? And the transformer turns ratio happens to be the square root of the impedance ratio. So that sounds like some hairy things there. Okay, what's the square root of the turns ratio? Okay, 600, or of the impedance, I should say. 600 ohm feed point impedance to 50, the square root of 600 over 50. And that works out, if you calculate it, to be about 3.5. It would be like a 35 turn primary and a 10 turn secondary. Now it's pretty easy to remember this, and that there's only one question like this in the pool. So if you just wish to memorize it, it's fine. Or if you want to take the square root of the two values that they give us and do it on your calculator, that's fine as well. But this is the only question like this in the chapter. So what are some techniques? Down at the bottom of the page here, I've got a couple of boxes here. Let's say that you want to be using an end-fed antenna. Let's say an 80-meter end-fed antenna. Okay, that's going to have very high impedance at one end of that wire. So we have to use a matching box, typically 9:1. There's other ratios that are used. A lot of times this is what it looks like. The coax from your transmitter would go in over here. The wire would get attached here. And then some people will put a counterpoise on this one or ground it. But most people just leave the other one disconnected. What does this look like inside? Well, it's a box with some turns around a fairly large toroid. The more power that you're going to run, the bigger the toroid has to be. So I just wanted to lead into this with a practical example. So coming back to the top, special RF impedance matching transformers are often used to equalize the impedances of the source and load to maximize the transfer of power to the load. So this end-fed half-wave wire has got a very high impedance where it's connected, but by using this transformer, we will bring that down to something close to 50 ohms to keep the transmitter happy. Two other ways of doing it. There's pi LC, inductance and capacitive pi networks, which we'll be showing you in the next slide. Then there's a trick that Gary's going to be talking to us about where you can use a length of coax between the transmitter and the load, or the antenna, of a certain length and a certain impedance in order to make everything happy. So these are the three techniques. So this sounds like an all of these question coming our way. Let's see if that turns out to be the case. So impedance matching circuits are often LC circuits made up of inductors and capacitors. I'm going to go back over to the telestrator again. So this is called a pi network, and you can kind of see why, because it looks like the Greek letter pi. Okay, a T network, you can see that it is configured like a T. So that's a pi network and a T network, and by selecting different values of the capacitor and inductor, you can make this tune just about anything. Back to the slide again. These are shown as fixed values here, but quite often any of these parts may be variable, so that you can use this impedance matching across multiple bands. So impedance matching circuits are often LC circuits made up of inductors and capacitors. That's what they look like. Okay, right on to some questions. We're moving through this fairly quickly, but that's a good thing. Which of the following devices can be used for impedance matching at radio frequencies?
Alpha.
Delta.
Alpha is correct. Bravo is correct. And delta is correct. This was all of these choices. And Charlie is correct. So read carefully, as Gary likes to say.
And when they're talking about that length of transmission line, that's not just another 50 ohm transmission line. That's a different impedance. We'll talk much more about it.
Yep, exactly. But what you need to know for now is that if there's more than one that's correct, it's probably going to be in all of these, which it is. What is one reason to use an impedance matching transformer at a transmitter output?
Bravo.
It is Bravo, to present the desired impedance to the transmitter feed line. Or as I like to say, you keep the transmitter happy. What transformer turns ratio matches an antenna's 600 ohm feed point impedance to a 50 ohm coaxial cable?
Alpha.
It is alpha, right? Or you could do to get to that, you could do the square root of 60 over 50, but I think you'll be able to remember this one. Okay, good. We're moving on into the next section now, active components. Now, semiconductors. We're going to be talking more about this in other lessons, both now and in the extra class, but I'll give you a highly simplified version for now. So in semiconductor components, typically, most semiconductors today, diodes and transistors, are silicon. Now, the element silicon is actually an insulator. So how could we make diodes and transistors out of insulators? Well, we do something called, we add a chemical to the material, to the silicon, to cause it to have excess electrons. I guess that's the easiest way to say it. So we've got excess electrons over here, so they're going to be willing to combine with something else. Over here, the way that we dope the other side, we use a chemical that causes an absence of electrons, also known as holes. So we've got holes, we've got electrons, and the electrons would very much like to fill those holes. And you can see that we've got something coming our way called current flow through this material. So this is P, an N-type material. P has the holes, N has the electrons. And a junction diode occurs when we take some P material and N material and kind of squish them up against one another. So a junction diode uses the PN junction to block the flow of current in one direction only. So this effect that we're seeing will only work one way. We push these toward each other and current can flow across the junction. If we reverse that polarity, this becomes wider and no current can flow. Giving you a highly simplified version of this right now. So current flows when a positive voltage is applied from the P-type to the N-type material, which is also called forward bias. We're showing a battery here. This is the symbol for a diode. The cathode corresponds to the negative side, or the N side, anode toward the P side. This is what it would look like in a circuit diagram. And there are two pool questions that ask about forward voltage. Now, when the diode is conducting, when it's forward biased, we've been talking about silicon, it takes a certain minimum amount of voltage for this current flow to occur and to continue. With silicon, it's about 0.7 of a volt. Germanium is another flavor of crystal that has a forward voltage of 0.3 of a volt. We had a student in a past class that had kind of a unique way of remembering this. I don't know if it'll work for you, but this is what she did. She substituted the R in germanium for a 3, and the L in silicon for a 7. So this is a way that she could remember that germanium was 0.3 of a volt, Ge3 manium, silicon is Si7 ilicon. Okay, if one were to try to pronounce that. So if that helps you, it's free. Otherwise, you'll have to memorize it. I hate memorizing things. So diode ratings, I don't see any blue text here, but it's kind of nice to know some of these things because you're going to be running into them. I suppose we could have called this slide how to blow up a diode, okay? So let's talk about that. Peak inverse voltage, okay, this is the maximum reverse voltage before breakdown occurs. So the diode, here's a bunch of different appearances of what you might find. If you exceed the voltage rating of the diode, the peak inverse voltage, you can actually arc across the P and the N side and short out the device, you destroy it. Average forward current, we saw that we had a 0.3 of a volt or a 0.7 of a volt drop. So there's some amount of, you might say, equivalent of resistance. So with enough current through the device, it's going to get hotter and hotter. So diodes have an average forward current, or maximum average forward current rating. Exceeding the diode's rating will destroy the diode's internal structure due to heat. It'll melt it. And then this isn't how to destroy a diode, this is just another factor. Junction capacitance. I mentioned that when a diode is reverse biased, it pushes the depletion zone apart, and that's like increasing the distance between plates on a capacitor. So junction capacitance, when reverse biased, the layers of P and N material act like plates of a small capacitor. The larger the voltage, the wider the plates are pushed apart, making a voltage variable capacitor. So the more voltage, the capacitance changes with it. This is the principle of what's called a varactor diode. Now, why is this important? Well, varactor diodes are used to modulate FM transmitters. We'll get into that more later, but this is just a little insight into how that works. So also another little factoid, junction capacitance affects the switching speed. Sometimes you want to use diodes to cause a switching of RF currents. And pin diodes are diodes that will allow a transmitter to switch quickly between transmit and receive without having to use relays. So just some things that you may run into. So this is just called all background and context, because you're going to hear about all of this stuff later. Here's some diode types. All kinds of things. When scientists first found out the effects that were created by diodes, they pushed it and pushed it and pushed it to find out all kinds of other properties. So a pin diode, and we don't need to know any of this for the pool, pin diode, low forward voltage drop, used for RF switching. A Schottky diode, which you may have heard of, low junction capacitance, allows for high frequency operation. Varactor, we talked about this, when reverse biased acts like a variable capacitor. And then our friend the Zener diode, we had to identify this on a circuit diagram last week, I believe. It's used as a voltage regulator. It has the magic property when it's reverse biased, it'll break down in a certain way that will hold the voltage absolutely constant. Good for reference. We didn't talk about light emitting diodes, but a diode, when it's forward biased, will actually emit photons. That's how light emitting diodes work. So this is all stuff that science discovered once they learned about the diode effect. All right, moving on. What is the approximate forward threshold voltage of a germanium diode?
Bravo.
Bravo, 3/10. What is the approximate forward threshold voltage of a silicon junction diode?
Charlie.
It's Charlie, 7/10 of a volt. These can be good troubleshooting aids too, because if you're working on a circuit and you don't know if it's working properly, if you measure the voltage across a diode or a PN junction and a transistor, you would expect it to be about 7/10 of a volt if it was forward biased. If it's 0, it means probably the part is shorted out, or if it's something else, probably something wrong in the circuit. So these are useful numbers. Now we're going to talk about transistors. Invented in 1947. Some of us weren't around back then, including me. Transistors invented by Bell Labs. So they have the property of being able to amplify. We'll comment on that a little bit more as we move along. But their high amplification makes them useful as switches for voltage and current. So if we can get a transistor to turn on all the way, that would be like close to it. You have a low voltage across the collector and the emitter, which would represent the logic 0. Saturation, when further increases in input result in no output change. So the transistor, it's fully on, it's saturated. It's cut off when the input signal reduces the output current to 0. So we've provided two cases now. Either the transistor is turned on all the way, that's saturation, or it's completely turned off, that's called cutoff. You can kind of start to see where 1s and 0s could be associated with these values. Saturation and cutoff are the operating points for a bipolar transistor used as a switch. They're also used as amplifiers, but we're just talking about switches right now. A picture of that here. Here's a closed switch, here's an open switch. So when the transistor is fully on, it's at saturation, and it acts like a closed switch. When the transistor is fully off, that's the cutoff state, it acts like an open switch. So we could associate these with logic values like 0 and 1, or 1 and 0, depending upon how we define them. A little bit more on bipolar transistors. I've got two pictures here. And a long, long time ago, somebody gave me this little trick. We don't really have to identify them for the general material, but and this is an NPN transistor. And somebody told me if you can think of that as being a not pointing in, the arrow is not pointing in, it makes it an NPN. Or for a PNP transistor, the arrow is pointing in, PNP. So that's how you can differentiate between a PNP and an NPN. And Gary had another trick that I learned, and that's that the arrow is always pointing toward the N material. So that's another way, and that'll come in handy a little bit later. So there's three connections to a bipolar transistor. We've got the emitter, the base, and the collector. For a PNP transistor, PNP, see how that lines up? Emitter, base, collector. Collector is typically output, base and emitter, and it's the flow through the transistor from collector to emitter is controlled by the current between the base and the emitter. So an analogy that I like is like a fire hose valve. A fire hose, you have a valve on it that will let you control the output of that hose. It can be up to 100 pounds per square inch. You couldn't possibly put your hand over the end of that hose to regulate the amount of water. Well, we have an analogy here where a small amount of current between the base and the emitter can control a much larger flow of current between the collector and the emitter. And the polarities are just opposite with the other case. Here's some pictures. There's all different flavors. This one here would be used in a high power application. See, it's got a heat sink there. There are tabs that could be screwed onto a heat sink. There's a smaller version that would go to a heat sink, and then little bitty ones. It all happens to be how much power you need to handle by the transistor. So we saw very little base emitter current is required for the collector to emitter current to flow. Control of a larger current by a smaller current gives you the concept of gain. So we're putting in a small current and we're amplifying that to a much larger current. And current gain in a transistor is known as beta. We haven't had any blue text in a while. Then we've got field effect transistors. And the same Gary's trick of the arrow pointing toward the N material works for us here. That'll become important later in life here. So this is a field effect transistor. We've got a junction field effect transistor, or JFET. It's got some P material as a substrate, and it's got an N channel, and then P for the gate. So these are the internal components. 3 electrodes, drain over here, source over here. So we're going to be wanting to pass current from the source to the drain. Then we've got the gate in the middle. The gate, the voltage on the gate, will control how much current can flow through this channel. So we got drain, source, and gate. And in the case of a junction transistor, which we saw previously, it was the current between the base and the emitter. This time we're controlling the device by the voltage between the gate and the source. So one was a current device, this is a voltage device. Then there's a special kind of FET called a MOSFET, metal oxide semiconductor. It's constructed by insulating the gate. Here's the gate, insulating the gate with a thin layer of oxide. So for a standard junction field effect transistor, they're actually touching. For a MOSFET, they're actually insulated by this thin gate. Now you can imagine if the gate is insulated from the channel, it's going to have a fairly high impedance. Note the blue. And write down some questions. We are just skimming the surface here. There's tons and tons of information behind all of this. They're in the reference material I shared on that second slide, and we'll get into this in more detail in future classes, especially when we get to the extra. So just from what we've talked about, what are the operating points for a bipolar transistor used as a switch?
Alpha.
Yes, saturation and cutoff, fully on or completely off. Which of the following describes MOSFET construction?
Bravo.
Yes, the gate is separated from the channel by a thin insulating layer. Vacuum tubes, wow, that was easy. All right, so I've listed some here, made some pictures. You might see this in an old radio. This would be probably in the receiver section. And then to contrast that with a humongous tube, I found a picture of a 3CX 1500, which we'll talk about in a second. So this is a circuit diagram of a tube. And you might be wondering, why do we, I mean, tubes are, you know, so 1950s, right? We don't really, why do we even care about tubes? Well, the reason is that there's still many amplifiers, power amplifiers in the amateur radio market that use tubes. The reason for that is that getting power, if you want 1,000 or 1,500 watts of amplification, it's much cheaper to do that, even today, with a tube amplifier than it is a solid state amplifier. So there are lots and lots of tube amplifiers available new in the amateur market and used, of course. So we need to know something about it. So all amplifying tubes have at least 3 electrodes. And those electrodes are a cathode. And the way this works is there's a heater inside. Somebody said once that real ham radio glows in the dark. Okay, what they were talking about is you can actually see the filaments in these glass tubes glowing kind of an orange color. So that works. In this case, we're inside a ceramic material. You can't see anything. So vacuum tubes typically operate at hazardous voltages. Now, for these type receiving tubes, it might be 150 volts or so. A high-powered transmit tube, that could be up to 4,000 volts. DC.
Klystron. Don't they call that a klystron?
No, this is not a klystron. It's actually a triode. A klystron is something entirely different. Yeah, Gary's going to talk.
Well, I'm just going to say klystrons are used UHF and up, and they're kind of a magnetically controlled vacuum tube. It's a specialty tube for high power output. But no, these are conventional tubes that we're looking at here.
Tubes, right. But we need them because they're in power amplifiers and they require really high voltage if you're going to have that much power. So you can see the difference. And this actually has air fins that air can be blown through. The ceramic material won't melt and all of that. So the elements are the cathode and the heater. I was talking about real ham radio glows in the dark. Well, this gets hot and actually boils electrons, if you want to look at it that way, off special coated material on the cathode. So that happens. Then the control grid, if this is negative, it's going to either repel the electrons back toward the cathode or slow them down as they're trying to get to the plate. And the plate typically has some kind of high voltage, 100 volts up to 4,000 volts, depending on what you're using it for. We're going to see what the screen grid does on the next slide. So here's a little background of what they are and how they work. And then coming into the pool question, so we've got the filament or heater. Typically that runs 6 volts or 12 volts in receiving tubes. Heats the cathode, causing it to emit electrons, or boil them, as I like to say. So the cathode is the source of electrons. The control grid, regulates electron travel between the cathode and plate. The screen grid, now remember when we were talking about capacitors last week? Capacitors in series decrease the total value of the capacitance. All right, here's an application. The screen grid, the primary purpose of a screen grid is, oh, I missed, okay, I gotta fix that. Reduces grid to plate capacitance. So consider a little capacitor here between the control grid and the plate. Well, we've got a kind of a parasitic capacitance, if you want to call that, between the control grid and the screen grid, and between the screen grid and the plate. So we've reduced the amount of capacitance between the grid and the plate. So let's look at this again, see if it makes sense. Screen grid, primary purpose of the screen grid is to reduce grid to plate capacitance. And then, of course, the plate collects the electrons.
And when you have a screen grid, you have to separate the control grid further out so that distancing also reduces the capacitance.
Yeah. Yeah, the manufacture and physics of how they make tubes is a fascinating area, but we won't get into that. All right, right into some questions. Again, we're just skimming the surface on this stuff. Which elements of a vacuum tube regulates the flow of electrons between the cathode and the plate?
Oh, no. Alpha.
Control grid, yes. Correct, alpha. What is the primary purpose of a screen grid in a vacuum tube?
Alpha.
Alpha, to reduce the grid to plate capacitance. And that's all there is to that particular piece. All right, so let's move on. We're going to increase complexity now and talk about analog and digital integrated circuits. So we've gone from resistors and capacitors and inductors and talked about semiconductors and tubes, and now we're going to talk about analog and digital integrated circuits. So we're going up the food chain, so to speak. So analog ICs are sometimes called chips, used in amplification, filtering, measurement, and power control, so lots of applications. A linear voltage regulator is an analog IC used to maintain a power supply output at a constant voltage over a wide range of currents. Now the concept of analog, which I've bolded here, means that it's operating over a wide range of values. It's not just an on or off kind of thing like logic gates are, which we're coming to. So this is one type. So here's an analog IC. This one says 7805 on it, which means that it'll regulate to 5 volts DC when put in a circuit the correct way. Another type of analog IC is an operational amplifier. Now the 741 op amp, or operational amplifier, probably the most prolific that's out there. You can get these for pennies. Find them at Hamfests in bags. Operational amplifier is an analog IC used for DC and audio circuits. Again, it operates over a wide range of values. That's what makes it an analog part. We also have RF. Let me back up just a fuzz. These are all lower frequency devices here. We also have integrated circuits that operate at much higher frequencies. RF ICs, low-level high-gain amplifiers, used as mixers, modulators, demodulators, and filters. And one form is called a MMIC, monolithic microwave integrated circuit. It works all the way up through microwave frequencies. Now I've got a question for you. Does anybody have a MMIC in their pocket right now? What do you think? Gary's holding up his cell phone. Yeah, your cell phone is full of MMICs, all right? So yeah, you've actually got MMICs in your pocket right now if your phone is in your pocket. Here's a blown up picture of one. It's the only question. Continuing with digital integrated ICs, they operate with, now these are digital. The ones that we saw before were analog, okay? Voltage regulators and amplifiers. Another amplifier used at high frequencies. Now we're getting into digital integrated circuits. These operate on ones and zeros rather than a wide range of analog values. Operate with discrete values of voltage and current representing the binary number system values 0 and 1. This kind of links back to our saturation and cutoff switch examples that we were looking at with transistors. An advantage of using the binary system is that ones and zeros are easy to represent by on and off states. It's called Boolean algebra. Okay, that actually was invented way back in the 1800s before we had any idea that any of this might be possible. Digital circuits can perform computations or control functions. And the modern chips, because we need to have a low power, use a technology called CMOS, complementary metal oxide semiconductor. It's a technology, it's popular because of its high speed and low power consumption. So you can have literally thousands and thousands of transistors on one of these large-scale integrated circuits. Now before CMOS, we had something called TTL, which is transistor logic, and that took much more power. So that's the reference that's being made to low power consumption. And there were logic families before transistor logic as well, but we don't need to get into those. All right, we flew through that. What kind of device is an integrated circuit operational amplifier?
Analog.
It's analog, right. It operates over a wide range of values, input and output. What is meant by the term mimic?
Monolithic.
Monolithic micro.
Bravo.
There you go, bravo. A monolithic microwave integrated circuit. And notice they were very crafty in how they did the rest of these answers. Wrong answers are called distractors, by the way. So these distractors, somebody spent some time inventing things that would sound plausible, but you want it to be monolithic microwave integrated circuit.
Yeah, microwave.
So what did I say?
You said it
Oh,
right,
okay,
but
yeah.
I just want to emphasize that these things, these devices will work up to microwave frequencies.
Yeah, amazing how technology has moved forward. Amazing that we can even have cell phones. Which of the following is an advantage of CMOS integrated circuits compared to TTL integrated circuits? Low power consumption, exactly. Now we're going to move into something that's going to look scary, but there's only one pool question, so hang on to your hat here. We're in digital logic basics. If you want to see this diagram in a little bit bigger format, it's page 4-31 in your book, if you care to turn there. So here's some different kinds of combinations of logic gates and some of the functions that they offer. So just giving you a quick overview. I'm going to blow up this particular one here because it's the only one where we have a pool question called an AND gate, and expanding on how that works. The basic building blocks of digital circuits are called gates. We have and or functions, and truth tables explain the Boolean functions implemented by the gates. Now Boolean, that's the algebra that deals with ones and zeros. So here's the AND gate, and I like to think of this to identify it. This looks like the letter D here, right? And the way that it works is described by what's called its truth table. So we've got these inputs, A and B, output C. So notice what happens here. Only in the case of A being 1 and B being 1 is C being 1. So the concept of AND, if A is high and B is high, then C will be high. So that's the concept of AND. The concept of OR, I'd like to look at this one and see the curve on the input and select the letter O, OR gate, AND gate. In this case, if A or B is high, then C will go high. So this one, A and B had to be high for C to go high. This one, if A or B is high, then C will go high. And that's defined here in the truth table as well. So this is the only one you need to know about. The function of a 2-input AND gate, output is high only when both inputs are high. A and B causes C to go high. All right, that wasn't so bad, right? One more concept, no questions here, but something that's helpful to know. There's something called inversion. In this case, we've got a triangle with a little circle on the output. What that means is it'll invert the signal. So if A is high, B is going to be low. If A is low, B is going to be high. Some people will call this an inverter or a NOT gate. And here's an inverted NAND truth table over here. So remember we said before if A and B were high, C would be high? Well, because the output is inverted, if A is high and B is high, then the output goes low, just the opposite, because it's of the inversion symbol there. Don't need to know that, but this is, as we get into more digital logic in future lessons, this will be really good foundational material for you. Now, gates in combination. Here's where we start doing some really useful things with some of the things we've talked about. So there's something called a flip-flop, and it has 2 stable states. I'm just thinking foot up, foot down. No, not that kind of a flip-flop. 2 stable states to a flip-flop. Sequential logic built on flip-flops, feeding other flip-flops used in counters. And I'll have a picture of those coming up. So a flip-flop has 2 stable states, the output being high or the output being low. And we're capable of switching that with sequential pulses coming into the flip-flop. So a 3-bit counter, we're going to start doing something with this now. A 3-bit counter means one that has 3 flip-flops connected, and I'll show you a picture of that coming up, can count 2 to the 3rd power or 8 in different states. It's 2 times 2 times 2. Might not connect yet, but it will in a second, I hope. What about a 4-bit counter? Well, that's going to be 2 times 2 times 2 times 2, or 2 to the 4th. 16 different states are possible. Then we have the concept of a shift register. Now we're going to feed bits into this shift register. We'll start out with a 1. Then every time we clock the register, it's going to shift everything to the right and shift it again, shift it again. After this happens 4 times, the bit that we started with is going to fall out of the shift register and go into what's lovingly called the bit bucket. Okay, it won't exist anymore. So shift register is a clocked array of circuits that passes data in steps along the array. Now, why might this be useful? Well, we're feeding it in serially, and after we've clocked it 4 times, we've got these 4 bits in parallel. So this could be a serial to parallel converter, for example. So let's take some of these things, grab the blue text, and see what that looks like over here. So here we've got our 3 flip-flops, and every time we clock this, it's going to move forward. This is a picture of what the gates that comprise a flip-flop. We've got 2 AND gates here, a clock signal, a J and a K signal. And you can dig into that a lot more if you want to Google it or look at the supplementary material. This is how they're configured. We're moving toward microprocessors. Okay, we started out with transistors, 1s and 0s, saturation, cutoff. We moved to digital logic gates like AND gates and OR gates. Now we're going to combine thousands of these together to wind up with a microprocessor. So a microprocessor is a computer on a single integrated circuit, capable, in mind-blowing time here, capable of performing millions of instructions per second using combinations of digital logic states. So all those AND and OR gates and all of the other things, using all of that, very high speed, has parallel and serial output ports. Here's the CPU and here's some of the ports coming out of it. It has counters and timers built in. Usually depends on external memory chips like random access memory and read-only memory. And nearly all built from CMOS logic. There are so many parts here that they get way too hot unless they were using CMOS. All right, now we flew through that. All right, so let's move on. Some questions. Which of the following describes the function of a 2-input AND gate?
Bravo.
It is Bravo. Output is high only when both inputs are high. So A and B cause C to go high. How many states does a 3-bit binary counter have? It is Charlie. So 2 to the 3rd power mathematically, or 2 times 2 times 2, which is 8. We multiply 2 3 times. What is a shift register?
Alpha.
It is alpha, a clocked array of circuits that passes data in steps along the array. And then we're going to move on to displays. See how we're flying through this? And you're getting them all right, too. Visual displays. Okay, visual displays, we can have an indicator. That means it's like a pilot light on the front panel of a piece of equipment, an on or off LED. We can have a display that's capable of presenting text or graphics. So a visual display can be just a simple indicator, or it can actually be displaying text and graphics. Now, light-emitting diodes, one type of indicator. An LED is a special diode that produces light when it is forward biased. It's available in multiple colors. And the history of these is pretty fascinating. They worked and they worked and they worked to get all of the colors that we had, that we have available today. A lot of chemistry there. So a diode has to be forward biased. It has to be conducting in order for it to create light. Low power consumption, fast response time, long life. These are all things that we get with an LED, light emitting diode. Liquid crystal display. These are interesting devices. They create it by sandwiching a liquid crystal material between two transparent glass panels. Then when voltage is applied to the electrodes on the front panel, the liquid crystals twist and block the light. Liquid crystal displays require ambient or backlighting since the liquid crystal layer does not generate light. That is super important. Liquid crystal display compared to an LED display, higher contrast and higher ambient lighting. And the way that I like to think of this is that we're not competing with the sun. With an LED, it's creating light, and if we have bright sunlight on the display, it might wash it out. But in the case of a liquid crystal display, this is light blocking, so it's a lot easier to read this in bright sunlight. So hopefully those words will make more sense now. All right, more questions. How is an LED biased when emitting light? Delta, forward biased. See, we're getting easier and easier as we go. How does a liquid crystal display compare to an LED display?
Alpha.
Alpha, higher contrast and high ambient lighting. You'd have a real hard time reading your TI-36X Pro in the dark. Be another way of thinking of that. All right, now we are to the point where it'd be a really good thing to take a break at this point. We've been going for a little bit over an hour, so we're going to get into practical circuits, some of the things listed here. And we're past the hardest part of this evening, so things will be easier going forward. There's a few things that look hard in the very next couple of slides, but the rest of it gets super easy. So hang in there, take 5 minutes, and get your mind off this for a little bit. See you in a few. So here we are in the second half of Chapter 4, Part 2. So this will wrap us up for the night. We've got a couple of sections to go through here. So here we've got Section 4.6. See the items that we're going to be talking about. First couple slides are the most complicated, but they're not very hard. Rectifiers and power supplies. We're going to talk about 3 different flavors, half-wave and full-wave rectifiers, 2 flavors of those. So a half-wave rectifier allows current to flow in 1/2 of the input AC waveform from the transformer. So here we have a transformer. Here's the input waveform, 360 degrees repeated. Here's a diode. Remember, the diode conducts in one direction only, so it'll just be conducting the positive peaks in this case. A characteristic, a half-wave rectifier, only one diode is needed. And these things are so cheap, though, that the other flavors are, there's not really much advantage here. This circuit will produce all kinds of hum. Notice how we've got all of these bumps here. They all produce hum, but this is the hardest one to filter. But the advantage is only one diode is needed. So we have 2 flavors of full-wave rectifier. We've got what's called a bridge rectifier, and you can kind of see this triangle form. That's a bridge configuration. And then we have something called a center tap transformer with 2 diodes. You don't see this version very much at all anymore because bridge rectifiers, these all come in one package, one integrated circuit, and they're super cheap. So, and we avoid the expense of the special transformer. So full wave rectifier, 2 types. So how does a full wave bridge work? Well, remember we saw back for the half wave rectifier, find him, the diode was only conducting on half the cycle. Well, wouldn't it be nice if we could cause the output to occur in between these humps? Well, that's what a full wave rectifier does. So here's the input waveform coming into the transformer. And what we're doing here, the magic is that 2 diodes will conduct, and this kind of explains it here. Kastler went through this as well. But on 1/2 of the cycle, we get one output. On the other half of the cycle, we're conducting through the other pair of diodes, and we get another output. We wind up with something that looks like this. So we have filled in those humps in between what we saw in the half-wave rectifier. So with a full-wave bridge rectifier, the output is produced during the entire 360 degrees of the AC cycle. The output, let's see if you can grasp this. Output is a series of pulses at twice the frequency of the input voltage. So we saw with a half-wave rectifier, these were happening 60 times a second. Because we've filled in the humps in between, now we have these outputs happening 120 times per second. So output is a series of pulses at twice the frequency of the input voltage. Much easier to filter, and you're not wasting half of the waveform. But we still have a problem with it being bumpy. Okay, we need to filter that. Rectifier's pulsed output is unstable or unusable as DC because of the ripple. If you were to hook up this kind of a full wave rectifier to an audio circuit, for example, you'd hear nothing but hum. So we use filters networks made up of capacitors and inductors to smooth out the ripple. So here's output of the rectifier, a coil and a capacitor. A lot of times you'll just see big capacitors because coils are expensive. Excuse me. So a common method to smooth the ripple in power supply is to use a large electrolytic capacitor, either inductor and capacitor or a large electrolytic. Now high voltage is a serious thing because remember we said that you could have 2 amplifiers that might have up to 4,000 volts of DC. So the concept here is to use something called a bleeder resistor. So here we've got a high voltage power supply and filter. And then we've got this bleeder resistor right here. And its purpose in life is it doesn't take a lot of current because you want most of the current to go to your load, but it's drawing enough current so it will discharge this capacitor over time. It might take half an hour for it to get down to 0, but it's a huge safety item. Most people that work on these power supplies will always short out those output capacitors before they get in there and start poking around because we're talking lethal voltages here. Of course, we have fuses to protect the power supply against short circuits. That's the concept of a bleeder we talked about. And even if the supply is unplugged, it's going to take a while for that to bleed off. Now we've got this little bitty power supply down here and this great big power supply over here. Let's talk about those. So switch mode power supplies. What's happening here is we're using transistors to switch rectified DC at a very high rate, actually converting it into a square wave between 20 and 50 kilohertz. Now remember that we've got 60 cycle AC coming out of the wall. If we can rectify that and then chop it up, making it a square wave, we can use a much smaller transformer at this higher frequency to play some games with it. So this high frequency operation allows the use of smaller components, meaning lighter weight and much less cost. So linear suppliers are very heavy due to their large iron core power transformers, and therefore cost a lot more. These two pictures that I have here, this PowerWorks SS30DV is a switch mode power supply. It weighs about 3 pounds. It'll put out 25 amps continuous, and this is the supply that Elecraft recommends for all of their radios, even their K4, their high-end radio. Say if you need a power supply for that, this is the one we recommend. And then this is an Astron RS35M. This is a linear power supply, much, much bigger. It will also put out 25 amps continuous, 35 amps peak. And in terms of weight and cost, the PowerWorks, it weighs about 3 pounds, costs about $140. The Astron weighs about, let's see, I've got that noted here someplace. It weighs about 30 pounds and costs a whole lot more money. It's about triple the cost. So some hams are very particular here. They won't use switch mode power supplies because of that high frequency switching that's happening. And that high frequency switching can cause noise across multiple ham bands. But if the power supply is designed for ham radio use, it can be perfectly clean, as to me proven by Elecraft's recommendation of this for their high-end radios. So they're good to use if they're designed for ham radio use. Much smaller, much less expensive, and just as good. Some hams, though, because the early switchers did have a lot of hash that got out, will only use a what's called a linear supply. But you don't have to do that. Here's a picture of one. We start with 120 volts AC. We immediately rectify it. No transformer. We're coming right out of the wall, and we're rectifying it. There's some filter capacitors, and then here's our switching transistors. They take this output that we've rectified and chop it up into much higher frequency output than what's coming in from the wall, like 50 kilohertz. And then there's what's happening here. We're going into a transformer, full wave rectifier. We filter it, and then we sample the output. And then depending upon what we have for an output, let's say we want 13.8 volts for our transceiver, if it matches that, or if it's too high or too low, then there's a control circuit here that will cause the pulse wave, or the pulse width of the switching to change, and possibly the frequency, to bring us back to 13.8 volts. So that's the concept, anyway, of how switch mode power supply works. Now it's important because we have 120 volts right from the line. We don't want any chance of that showing up on the output. So typically we have isolation between this output and the input. So that's just the concept of high frequency, smaller transformer, less weight, less cost, that does have the potential for RF noise. And right into some questions. What portion of the AC cycle is converted to DC by a half-wave rectifier?
Bravo.
Bravo, 180 degrees. What portion of the AC cycle is converted to DC by a full-wave rectifier?
Delta.
Delta, all 360, those double humps. What is the output waveform of an unfiltered full-wave rectifier connected to a resistive load?
Alpha.
It is alpha. A series of DC pulses at twice the frequency of the AC input. So we're putting little humps between the humps. You like my technical language here? What is characteristic of a half-wave rectifier in a power supply?
Alpha.
Alpha, only one diode is required. What type of rectifier circuit uses two diodes and a center-tapped transformer?
Bravo.
Okay. I might not have spent much time on this, but it is the full wave circuit. The other one is the full wave bridge, where we have 4 diodes. The key here is type of rectifier that uses 2 diodes in a center tap transformer. That's the full wave. The bridge uses four diodes. Which of the following components are used in a power supply filter network?
Charlie.
Charlie, capacitors and inductors. What is the function of a power supply bleeder resistor?
Bravo.
Well, Bravo seems to be the predominant answer. Discharges the filter capacitors when power is removed, which reduces shock hazards, but not from induction coils. That's what makes C incorrect. Which of the following is characteristic of a switch mode power supply as compared to a linear power supply?
Charlie.
Charlie, high frequency operation allows the use of smaller components. Right. Now getting into batteries and chargers. It gets easier and easier as we go along here. So we're talking about large marine. These are usually lead acid batteries, can be used as backup. And if you discharge them too far, it'll damage the battery, it'll reduce the battery life. And this answer is controversial. What you want to answer when you get to this in the pool question, the minimum allowable discharge voltage for lead acid batteries is 10.5 volts. If you go to Google and use their AI, it'll tell you that that's more like 12 to 12.2 volts, so that this is really too low. And Kessler had differed with this as well, but this is what you need for the exam question, 10.5 volts. The batteries, used to be everything had NiCads that was available back then. So an advantage of batteries with low internal resistance is high discharge current. So these battery chemistries all have low internal resistance. Lithium iron phosphate is extremely popular. This is one that I have. And batteries do over time self-discharge. That's why you should store them in a cool, dry place. This is an interesting chart I just put up for information. Notice the average of the energy rating. The ones that are high are alkaline and lithium. Notice these big numbers? That's why they're so popular. And look at this one, 14,000 milliamp hours. That's an alkaline D cell. You don't see those except in flashlights anymore. But I just thought this was interesting to compare the different battery technologies and what kind of energy you could get out of them. All right, what is the minimum allowable discharge voltage for the maximum life of a standard 12-volt lead-acid battery?
Charlie. Charlie, but actually delta.
Yeah, Charlie for the purpose of the exam. What is an advantage of batteries with low internal resistance?
It's Bravo, I think.
Yeah, Bravo, high discharge current, low internal resistance. It can dump a lot of power in a hurry. Alternative power. Notice we've got a happy cloud and a happy sun over here. They're going to do some good things for us. So photovoltaic conversion, that's what happens with solar power, process by which sunlight is changed directly into electricity. And of course, wind generator, we've all seen these wind farms that are also controversial. It's a big propeller thing that drives a DC generator. This happens to be a battery backup. I used to be in the cellular business as a tech and installer, and we put in these humongous battery banks at some of the cell sites. So when wind is not there, or solar is not there, or the mains go down, we're depending upon these this energy storage. Wind and solar definitely require some kind of storage mechanism for when the sun is down or the wind is not blowing. Okay, some of this is a little bit dated, but that's all right. Solar cells are a special type of diode. Photons absorbed by electrons create a forward voltage across the diode junction. Open circuit of a solar cell is about 0.5 volt DC, so we wind up putting these in series and parallel to bump that voltage up to something that will actually be useful for us. So the configuration of individual cells in a solar panel, they happen to be connected in series parallel. So the individual cells will only put out 0.5 volt each. Some more blue text. Series diode should be connected between a solar panel and a storage battery to prevent discharge of the battery through the panel during times of low or no illumination. And the way this pretty much works today is that there's a charge controller between the solar panel and the batteries. But if you didn't have that solar controller, this would be true. For lithium iron phosphate batteries, a solar panel must have a charge controller. For lithium, batteries have to be very carefully monitored so that the individual cells will not overheat. So that's what the charge controller does. Questions. Why should a series diode be connected between a solar panel and a storage battery that is being charged by the panel?
Bravo.
It is Bravo, to prevent discharge of the battery through the panel during times of low or no illumination. What precautions should be taken when connecting a solar panel to a lithium iron phosphate battery?
Delta.
Delta, yes. The solar panel must have a charge controller. That ensures that all of the cells are charging the way they should. In what configuration are the individual cells in a solar panel connected together? Alpha, series parallel, correct. What is the approximate open circuit voltage from a fully illuminated silicon whatever that says cell, yeah, PV cell, photovoltaic.
Bravo.
Yeah. Now, moving on to connectors. We have connectors all over the place in a ham radio. Some of them are audio connectors. This is a famous RCA that you've got on your stereo. These are power pole connectors, which have become very popular. All of my radios have these on them because I installed them. And here's an example of a connector that can only be installed one way. Well, it's true of these too, because you don't want to ever get positive and negative reversed. So the connectors are typically keyed, so that's not possible. So plugs are usually on the cables, jacks on the radio, all kinds of things. Hams typically will have a whole box full of adapters, so you can get one connector type to another. And we talked about the keyed connectors. Audio connectors, you would recognize these from some of your stereo equipment. Here's a Y connector, like we'd use at field day, so two people could listen with headphones to one radio. Just all kinds of connectors. And many of those are used in audio connectors from the hi-fi world. Many of them are used in ham radio. This is the so-called RCA connector, RCA phono, commonly used for low frequency or DC signal connections to a transceiver. A lot of times some of the control signals for high power amplifiers are use RCA in the back of your transceiver. Then I'm hoping Gary can pronounce this for us, because I can't.
Deutsches Institut für Normung, the German Institute for Standards.
Yes. To us, it's a DIN connector. You'll see DIN connectors all over the place, but that's where it came from. And now that you know how to pronounce it, there'll be a test on that. Not really.
Sehr gut. Du hast es sehr gut gemacht.
Dankeschön.
All right, you guys, behave yourself. So these are quite often used for accessory circuits. I'm going to show you the back of my radio here, so we can see some of this. I use a 7610 as my main radio, and just identify these are DIN connectors here for accessory functions. Here we've got some RCA jacks used for amplifier. Here's some speaker outputs. These are 1/8 inch audio. We've got a LAN connector. It's an RJ45. We've got a DVI, digital visual interface. All of these crazy connectors are on the backs of our radios, and some USB, BNCs, and this is a Molex up here, Molex connector that operates with a tuner. So just reinforcing the fact that you'll have to deal with a lot of different connector types. I wanted to include this one because you'll see it so often, the famous TRS plug, tip, ring, sleeve. You can get these in 1/4 inch and 1/8 inch sizes. Sometimes we actually have 2 rings on them. You've seen this probably with some of your cell phones. Include a microphone connection. So the contact tip here, the ring, and the sleeve, or TRS connector or plug. This one actually looks like an adapter, where this is 1/4 inch here, and this is probably a 1/4 to 1/8 inch adapter. You'll see these all the time. I wanted you to know the terminology. Power connectors, it's a little bit, I think you can see it. So there's, we saw one of these on the back of my ICOM. Just all different flavors that you'll have here. Anderson power poles. You'll eventually probably want to be able to put these on your radio because they're so standard. You have to be careful when you mate them up, though, to have the polarity correct. More RF connectors and adapters, and hams will wind up with boxes of BNC to N and UHF to TNC and all of these crazy things. Now, a couple cool questions related to connectors. Not this one, though. This is the one that you're most familiar with seeing, called UHF connectors, SO239, PL259, the industry designations. Now, N connectors are moisture resistant and used up to 10 gigahertz. You can kind of see this little red seal inside. That's what makes it moisture resistant. Used up to 10 gigahertz. It's higher than our HF radios need. SMA, now you've probably got one of these on your handheld two-way radio, your 2-meter radio. SMA connectors are small threaded connectors designed for miniature coaxial cable and are rated up to several gigahertz. Usually don't need them that high for our handhelds. Typical upper frequency limit for low SWR operation of BNC connectors is about 4 gigahertz. So if you can just kind of capture these BNC, good to about 4 gigahertz. N-type, good up to 10 gigahertz. On high-end test equipment, a lot of times there'll be N connectors or BNC because of those high frequency capabilities. Just a second to look at the blue text. Then data connectors. It used to be our computers always had one of these serial ports on it. Now everything has gone USB. This is the famous DE9. We still have to do some interfacing with some radios to convert USB to this type of a connector. But pretty much everything modern is using USB these days. What is a typical upper frequency limit for low SWR operation of 50 ohm BNC connectors?
Charlie.
Charlie, that was the 4 gigahertz BNC. Which of the following describes an N connector?
Alpha.
Alpha, moisture resistant, up to 10 gigahertz. What is an SMA connector?
Bravo.
Bravo. Which of these connector types is commonly used for low frequency or DC signal connections to a transceiver?
C.
C, RCA phono. Then on to basic test equipment. So I've got a bunch of things here. Test equipment is one of my favorite subjects. I love fixing things. I used to be a two-way radio technician for a good many years. I worked for Motorola, and we helped service shops fix things that were stumping them. So I spent a lot of time with test equipment. So we've got analog and...
This chapter makes me miss Radio Shack.
Yes, it does. It does. Analog and digital multimeters, called a multimeter because it does multiple things: voltage, current, resistance. Will normally be your first piece of test equipment, and you can get them really cheap. This is a Gardner Bender. You can find those at your local Ace Hardware, usually. In some of the big box stores, only 20 bucks, but they're perfect for checking for fuses, and do you have 13.8 volts coming out of your power supply? So for simple little things, these are very functional. I have one of these, but I don't use it very often. So measures voltage, current, resistance. We got analog and digital. Here's an analog one. You can see the needle swings. This is digital. And Fluke has a very inexpensive digital meter called the 101, which isn't a bad thing to have. It doesn't measure current. Well, this is, that's what we were looking at, the 101. So that's the difference between analog and digital, okay, the display. And in terms of the pool, analog multimeters are preferred to digital multimeters when adjusting circuits for maximum or minimum values. So if you're adjusting a circuit, and let's say you're tuning a coil or something like that and looking for an output, it's easier to see the peak or the dip with an analog display than it is with a bunch of numbers bouncing around. Now, some of the better digital meters have a high speed display across the bottom that will simulate an analog display. So sometimes these are usable, but in terms of our poll question, they're saying analog meters are preferred to digital when adjusting circuits for max or min values.
Where's the Simpson meter?
That's one of these, okay, Simpson 260. Yeah, the good old, I've got more than one of those at home too. Analog and digital multimeters, okay. Now, an advantage of a digital, it offers better precision because it's easier to see down to the tenths or the hundredths here than you could possibly interpret on an analog display. So that's the reason for this one. And digital meters can have some really cool features. Auto ranging, you don't have to set 1.5 or 30 or 1500 volts. You know, this knob here, none of those numbers exist here. You just set it to AC voltage or DC voltage and it'll automatically find the range. Peak hold is a nice feature on some meters. And some of them will measure frequency capacitance, even have a temperature probe on them. So some more differences between the two. When measuring voltage, the meter should have a high input impedance to decrease the loading on the circuit being measured. Now, anytime you connect a meter into an active circuit, some of the power from the circuit you're measuring is going to be absorbed by the meter, which could throw off the measurement or the function of the circuit. So that's the reason for high impedance, desiring to have a high impedance meter. When measuring voltage, the meter should have a high input impedance to decrease the loading on the circuit being measured. Now, I've got a go-to DVM that I use. It's the Fluke 117. And I just put this in here in case you've got this much money to spend. As I said here, your very first meter can be one that's very inexpensive, and that will probably meet most of your needs in the beginning days. The reason this has become my go-to, because it very nicely fits my tool bag, and I do some electrician type work, so this has some features optimized for that, like a non-contact voltage sensor, and something called a low Z AC voltage, which eliminates ghost voltages. Sometimes you're measuring a wire in a house to try to see if it's live, and you'll see that it says 120 volts, but it really isn't because it's voltage that's being induced by another wire that's running in the same cable. So that eliminates that problem. Auto ranging, min-max function. The only negative for electronics for one of these is you can't measure microamps. It's really, its market is really a general purpose electrical and electrician. So you can't read microamps. I've got other meters that'll do that though. This one's a little more expensive, about $252 I saw on Amazon today. However, the best DVM for you will be dictated by the way that you want to use it. One of those lower cost meters may be perfectly fine. All right, multimeters. Why do voltmeters have high input impedance? Charlie.
No, delta.
How about delta? Okay, now high input impedance, that has to do with loading down the circuit that you're measuring. The improved resolution, that's from a digital meter. There's a different question on that. What is an advantage of digital multimeters as compared to analog multimeter?
Charlie.
There you go.
There you go. That's a higher precision because it's easier to see those larger numbers or the smaller values from the long list of numbers. When is an analog meter preferred to a digital multimeter?
Delta.
Delta.
You're right. When adjusting circuits for max or min values, really easy to see.
And
Oscillo-
here, the pin clicking.
Yeah, if you hit it too hard, for sure. The oscilloscope provides a visual display. I kind of like to, I liken this to looking at a miniature TV. We've got vertical circuits and horizontal circuits. We've got, this is a sine wave here. So we've got the amplitude, which is how strong it is, and how fast it's moving by the horizontal, the time base. Oscilloscope is better than a digital voltmeter for measuring complex waveforms. So for something that's really hairy, like speech waveforms and single sideband, it's pretty tough to see what's going on with an analog meter, but a scope is excellent. Horizontal and vertical channel amplifiers associate the scope with the TV, and this will make sense. We've got horizontal and vertical going on here. External signals connected to the horizontal and vertical channel inputs to control the display. So that's what these connectors are for. You put a probe on there. And you can have variable gain and update rates. All of these other controls will adjust those timings for you. Now, if you ever looked at a product review in QST magazine, they'll normally have some pictures like this that show keying waveforms for CW. So an oscilloscope is the best instrument to use when checking the keying waveform of a CW transmitter. Now notice on this one how the rise time goes up gradually and then comes back down gradually. That way you don't have the equivalent of generating square waves and transmitting them. That causes all kinds of trash to go out with your signal. You'll have a wide key clicky signal, as it's called. So here's just two different versions of keying waveform. Then one more question here. The attenuated RF output of a transmitter may be connected to an oscilloscope to check the RF envelope of a transmitted signal. Now you don't want to connect your oscilloscope directly to your transmitter output because you might blow up your oscilloscope. So that's what they mean by the attenuated RF output of a transmitter through some kind of a coupling device. But then you can actually see what's going on with your transmitted audio. This would be the RF, the bright green, and the humps. This would be a sine wave modulating an RF carrier. And you can tell if it's distorted, if it's flat topped, or if it's over or under modulating by what you see in the display. For transmitter monitoring, a lot of hams used to use something like this. I've got one of these, but I don't use it, and I think Gary's got one too, probably in a box someplace. Some hams will just use an oscilloscope that they get at a Hamfest cheap if they want to monitor their transmit signal. Transmitter monitoring can be useful if you want to adjust keying waveforms. There's adjustments in your transceiver for doing that. And you can monitor what's going on. Okay, what item of test equipment contains horizontal and vertical channel amplifiers?
Delta.
Delta, an oscilloscope. Which of the following is an advantage of an oscilloscope versus a digital voltmeter?
Delta.
Delta, complex waveforms such as speech waveforms can be measured. Which of the following is the best instrument to use for checking the keying waveform of a CW transmitter?
Alpha.
Alpha.
That's our favorite oscilloscope. What signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal?
Delta.
Delta, the attenuated RF output of a transmitter. Okay, now we're going to get into some really useful things here. Not that any of what we've talked about so far wasn't. An antenna analyzer may contain an RF signal generator, frequency counter, SWR bridge, and impedance meter. This is the one that I have, Rig Expert. I really love it. This one here is made by, or was made by MFJ when they were in business. They had a tremendous line of SWR meters. So these connect to the antenna and feed line to measure SWR. So basically you'd pull the antenna connection off the back of your radio, take your transmission line and antenna, plug it into the antenna analyzer, and find out all kinds of interesting information about your antenna. Uses small signals and then gives you feedback on its resonance and impedance. So SWR measurements, impedance. Some models, like the Rig Expert, can actually measure the impedance of coaxial cable, velocity factor of cable, and electrical length, and time domain reflectometer functions. I really love mine. It also interfaces to a computer, so I can capture displays and take information to see if my antenna system is changing over time. This one is something that you might run into, strong signals from nearby transmitters. We're putting out a very weak signal and then checking how the antenna system is reacting by the weak signal coming back. If there's strong signals out there, like a AM transmitter in your neighborhood or close to you, that can really mess up the readings that you get. So strong signals from nearby transmitters can affect instrument accuracy. This is something relatively new, and I didn't really want to buy one of these because I already had an instrument that I liked a lot. These are pretty cheap. Amazon, 60 bucks, R&L Electronics, a little bit more. I've always bought this kind of equipment from R&L because I know that it's going to be the real deal. A lot of the stuff on Amazon, some of it is cheap knockoffs. You don't know if you're getting the good thing. But Gary influenced me here. He introduced me to this book, Nano VNA's Explained book. This is by the Radio Society of Great Britain, and there were so many things in this book that things that I could measure that I couldn't measure any other way. So Gary introduced me to this book, and then I had to buy the analyzer. And I'm glad I did. So be careful because
I love spending your money.
yes, yeah, you do well. YouTube is your friend. Tons of information on YouTube. These are much, much cheaper than those antenna analyzers that I showed you earlier too. So some people have avoided buying an antenna analyzer and just used the Nano VNA, but there is a learning curve. So here's some other instruments. The Bird 43, very famous watt meter. You can read forward power. Then if you reverse this slug, you just rotate it. You can read forward power, reverse power, and calculate SWR. Here's a couple of other boxes that will do the same thing. Field strength meter. This is an MFJ model. It's got two little antennas on it. And when you transmit, you can kind of see if there's anything that it's picking up. That's the idea of a field strength meter. Okay, which of the following must be connected to an antenna analyzer when it is being used for SWR measurement? In other words, how do you hook it up?
Delta.
Delta. Well, no. You need it. Charlie, yeah, you want to connect it to your antenna and feed line so that you can tell what your antenna and feed line are doing. So you don't want to connect it to your transmitter, you'll blow it up and it won't do you any good on a receiver at all. Which of the following can be determined with a directional watt meter?
Alpha.
Alpha.
Yeah, standing wave ratio, forward power, and reflected power, and then you can calculate SWR from that. What effect can a strong signal from a nearby transmitter have on an antenna analyzer?
Charlie.
No. Bravo, it's Bravo. Received power that interferes with SWR. By received power, that means power that might be coming from a local broadcast transmitter, AM broadcast usually. Which of the following can be measured with an antenna analyzer?
Charlie.
That is Charlie, impedance of coaxial cable. Front to back can't be done. Yeah, that's the only one that works. And that's the end of chapter 4. We've covered a ton of stuff tonight of varying levels of complexity, and hopefully the answers weren't too hard to get to. And please review this in the days and week to come. And we're into our class chat session here. And what are we going to do next week, Gary?
Chapter 5, radio signals and measurement. I took a look at my presentation. 388 slides, it's going to be a lot, but not a lot of math, but a lot of new concepts to consider.
Is that going to be done in 1 week?
In 1 week, indeed.
Okay, all right.
Next week, chapter 5.
All right. So read ahead and fasten your seat belt. Come next Tuesday, and all of our previous lessons are on the YouTube channel. If you go to the playlist, you can find it there. If you're frightened by the chapters, sometimes it's helpful to look at last year's presentation.
Any quick comments or questions before we go tonight?
I was wondering, is there any advantage to an analog oscilloscope rather than a digital one? Or?
Much easier to use, typically. So, and also you have a problem with digital scopes where you have aliasing problems if the frequencies are being measured or sampled at the wrong rate. However, there's all kinds of things you can do with a digital scope, like you can do frequency to, you can get a spectrum display from the analog input. You can store waveforms for analyzing them later. Tons of advantages to a digital, and you can get them. I think yours was under $400, wasn't it, Gary?
Yeah, I've got both analog and digital, and I used the digital one.
Yeah.
It was about $300 at a Hamfest.
Yeah, yeah. So yeah,
If you want really accurate readings, you measure on both, right?
you can. Yeah, you can. Yep. There's pluses and minuses to both, but most people, once they get into them, far prefer the digital scopes, and they're very affordable. Any other questions? Okay, I think we can
All right, we made
close it
to
off.
the end. Thank you all for tuning in and appreciate your participation. Thanks for the folks on YouTube. And until next week, 73.
I mean,
Thank you.
Thank you.
Yep.
Everybody.
Yep. See y'all.
Have a good week.